Many people believe that red stars are the hottest stars. After all, red is often associated with fire, heat, and danger. However, this common belief is actually incorrect. When it comes to stars, blue is the color of extreme heat, not red. In the vast expanse of space, stars come in a dazzling array of colors, each hue hinting at the incredible forces at play within their cores. Understanding the relationship between a star's color and its temperature is fundamental to unraveling the mysteries of these celestial objects. This essay will delve into the fascinating world of stars, debunking the misconception that red stars are the hottest. We will explore the scientific principles behind star color and temperature, revealing why blue stars reign supreme in the cosmic arena of heat. Prepare to embark on a journey that will illuminate the true nature of star temperatures and shed light on the fascinating processes that govern the lives and deaths of these celestial wonders. The color of a star is not a random occurrence, it is directly related to its surface temperature. This fascinating connection arises from a fundamental principle in physics known as black-body radiation. To grasp the concept of star color, we must first understand this intriguing phenomenon. Imagine a hypothetical object called a blackbody, which absorbs all electromagnetic radiation incident upon it. When heated, this blackbody emits radiation across a range of wavelengths. The peak wavelength, the wavelength at which the most energy is emitted, is inversely proportional to the object's temperature. This means that hotter objects emit radiation with shorter wavelengths, while cooler objects emit radiation with longer wavelengths. This relationship between temperature and peak wavelength is the key to understanding why stars have different colors. Hotter stars emit a significant portion of their energy in the ultraviolet and blue parts of the electromagnetic spectrum, resulting in a bluish-white hue. As stars cool, their peak emission shifts towards longer wavelengths, causing them to appear yellow, orange, and eventually red. Blackbody radiation is the cornerstone of understanding star color. This phenomenon describes the electromagnetic radiation emitted by an idealized object known as a blackbody, which absorbs all incident radiation, regardless of frequency or angle. When a blackbody is heated, it emits radiation across a continuous spectrum of wavelengths. The intensity of this radiation at each wavelength depends solely on the temperature of the blackbody. This is why a blackbody is often used as a theoretical model to approximate the radiation emitted by stars. The key to understanding star color lies in Wien's displacement law, a fundamental principle in physics that governs blackbody radiation. This law states that the peak wavelength of emitted radiation is inversely proportional to the absolute temperature of the blackbody. In simpler terms, hotter objects emit most of their light at shorter wavelengths, while cooler objects emit most of their light at longer wavelengths. This is why a piece of metal heated to a high temperature glows red, then orange, then yellow, and finally white as it gets hotter. Similarly, stars emit different colors depending on their surface temperatures. Among the stars that grace the cosmos, blue giants stand out as true behemoths. These stellar powerhouses are not only incredibly hot but also incredibly massive and luminous. Their bluish-white hue is a testament to the intense nuclear reactions raging within their cores. Blue giants belong to the spectral class O and B, characterized by extremely high surface temperatures, ranging from 20,000 to 50,000 Kelvin. These scorching temperatures result in the emission of copious amounts of ultraviolet radiation, making them some of the most energetic objects in the universe. Due to their immense mass, blue giants have a relatively short lifespan compared to their cooler counterparts. Their nuclear fuel, primarily hydrogen, is consumed at a prodigious rate, leading to shorter lifespans. Despite their fleeting existence, blue giants play a crucial role in the evolution of galaxies. They are the cosmic engines that synthesize heavy elements, enriching the interstellar medium with the building blocks of planets and life itself. Section 5. Red dwarfs, cool, abundant, and long-lived. On the opposite end of the stellar spectrum, we encounter red dwarfs, the most common type of star in the Milky Way galaxy. Unlike their blue giant counterparts, red dwarfs are small, cool, and incredibly long-lived. Red dwarfs belong to the spectral class M, characterized by low surface temperatures, typically below 4,000 Kelvin. Their reddish hue is a consequence of their relatively cool temperatures, which cause them to emit most of their light in the red part of the electromagnetic spectrum. Despite their small size, red dwarfs are incredibly dense and efficient at conserving their nuclear fuel. They burn hydrogen at a much slower rate than more massive stars, giving them lifespans that can stretch for trillions of years. Red dwarfs are fascinating objects for astronomers, as they offer a glimpse into the long-term evolution of stars and planetary systems. Their extended lifespans provide ample time for life to potentially emerge on any orbiting planets. Section 6. The Hertzsprung-Russell diagram, a stellar map of temperature and luminosity. To understand the diversity of stars and their evolutionary pathways, astronomers rely on a powerful tool known as the Hertzsprung-Russell diagram, or HR diagram. This diagram plots stars based on their luminosity and temperature, revealing fundamental relationships between these stellar properties. The HR diagram is a scatter plot where each point represents a star. The vertical axis represents the star's luminosity, or the total amount of energy it emits per unit of time, while the horizontal axis represents the star's surface temperature. The HR diagram is not merely a random scattering of stars. It exhibits distinct patterns that reflect the different stages of stellar evolution. The most prominent feature is the main sequence, a diagonal band that stretches from the upper left corner, with hot, luminous stars, to the lower right corner, with cool, faint stars. The position of a star on the HR diagram provides valuable insights into its age, mass, and evolutionary stage. By studying the distribution of stars on this diagram, astronomers can piece together the life cycles of these celestial objects. Section 7. Spectral classification, categorizing stars based on their light. Astronomers classify stars based on their spectra, the fingerprints of stars. Analyzing starlight reveals a star's chemical composition, temperature, and properties. The Morgan-Keenan MK system categorizes stars into 7 spectral classes: O, B, A, F, G, K, and M. These classes are ordered by decreasing temperature, with O stars hottest and M stars coolest. Each class is subdivided into 10 subclasses, from 0, hottest, to 9, coolest. Our Sun is a G2 star, a relatively cool yellow star. Spectral classification helps astronomers study stars systematically. Analyzing spectra unlocks information about stars' properties and histories. Section 8. Stellar evolution, from birth to supernovae. Stars, like living organisms, go through a life cycle of birth, growth, maturity, and eventual death. Stars are born in giant clouds of gas and dust known as molecular clouds. The intense heat and pressure at the core of a newborn star trigger nuclear fusion. Most of a star's life is spent fusing hydrogen into helium on the main sequence. As a star exhausts its hydrogen, it expands into a red giant or supergiant. Eventually it sheds its outer layers, leaving behind a white dwarf, neutron star, or black hole. Section 9. Conclusion. The significance of understanding star temperatures and colors. The study of star temperatures and colors is not merely an academic pursuit. It has profound implications for our understanding of the universe and our place within it. By unraveling the secrets of stellar evolution, we gain insights into the processes that govern the formation of planets, the synthesis of elements, and ultimately the origins of life itself. The color of a star is not simply a beautiful spectacle. It is a window into the heart of a star, revealing its temperature, mass, and stage of evolution. By studying the colors and spectra of stars, we can decipher their chemical compositions, trace their movements through space, and piece together the history of our galaxy. As we continue to explore the cosmos, our understanding of star temperatures and colors will undoubtedly deepen, leading to new discoveries and a greater appreciation for the awe-inspiring beauty and complexity of the universe we inhabit.